You know, every time you see a CT scanner or an X-ray machine, you're looking at a piece of technology that has, no exaggeration, saved countless lives. But deep inside that machine, there's one single part working under absolutely unbelievable pressure that makes the whole thing possible. So today, we're going to pull back the curtain on that unseen engine at the very heart of modern medicine. So, if you had to guess, what would you say that part is? I mean, is it this super complex software? Or that giant ring the patient slides through? Maybe the detectors? Nope. It's this thing right here, the X-ray tube. Honestly, the best way to think about it is like a super specialized, incredibly high-performance light bulb. But instead of making light we can see, it's designed to forge one of the most powerful tools in the entire medical world. Okay, so let's dive in and see how this incredible light bulb actually pulls it off. The whole process is this fascinating little dance of physics, and it all has to happen inside a perfect vacuum. It all kicks off with this tiny little spiral of tungsten wire. That's the filament, and it acts as the cathode, the negative end of the circuit. We run an electric current through it and heat it up to an insane 2700 Kelvin. To put that in perspective, that's nearly half the temperature of the surface of the sun. Now, at that crazy temperature, something pretty wild happens. It's called thermionic emission. The intense heat literally boils a cloud of negatively charged electrons right off the surface of that wire. It just creates this cloud of projectiles ready to go. And then, bam, we apply an incredibly high voltage across the tube. This creates this super powerful electrical field that just grabs that cloud of electrons and launches them with tremendous force across the vacuum-sealed gap inside the tube. These electrons just slam into a metal target on the other side. That's the anode, the positive end, at nearly the speed of light. And it's that incredibly violent sudden stop that forces the electrons to shed all their energy, and they release it as high-energy photons, which, you guessed it, we know as X-rays. But here's the catch. Creating X-rays this way comes at a huge cost. This whole process puts the tube under some of the most extreme conditions you can imagine for any piece of medical gear, which makes failure, well, a constant threat. Now get this, because this is the real kicker. For all that incredible energy and physics, only about 1% of the energy from that electron beam actually becomes useful X-rays. 1%. The other 99% is just converted directly into waste heat. So what that means is an X-ray tube is basically a high-tech furnace, and that heat is its #1 enemy. And all that heat and stress leads to a whole bunch of ways these things can fail. The bearings that spin the target, they can wear out and just seize up. The filament itself can just burn out, kind of like an old light bulb. The target can get these tiny little micro cracks from being heated and cooled so violently over and over. Or the seals can spring a tiny leak and poof, there goes your vacuum. And this right here, this is what that damage looks like in the real world. You're looking at an anode target that's just been hammered by thermal stress. It's pitted, it's cracked, and every single one of those little imperfections makes the X-ray beam worse, until eventually the whole tube is just useless. So for decades, engineers were in this constant battle with heat and bearing failure. But then a really clever innovation that was first developed back in 1989 came along and offered a pretty revolutionary solution. It's called liquid metal bearing technology, or LMB, and it's a total game changer. Instead of old-school steel ball bearings that grind against each other and create friction, LMB tubes use a super thin film of liquid metal. The moving parts never actually touch. They just glide on this liquid layer. Think of it kind of like a puck on an air hockey table. Let's just break this down side by side. With the traditional bearings, you've got steel-on-steel contact. That means friction, noise, and wear. Plus, they actually act like an insulator, trapping all that nasty heat right where you don't want it. But with liquid metal bearings, there's no contact, so you get zero mechanical wear and no bearing noise. And, this is the big one, the liquid metal actually helps conduct heat away from the anode. It also means you don't need to pause between scans to let the tube cool down. So what's the bottom line here? It's this number. By getting rid of the friction and doing a much better job with cooling, a liquid metal bearing tube can last more than double the lifetime of a traditional one. That is a massive, massive leap in reliability. And look, this isn't just some cool engineering fact. This one upgrade, in this one component, creates this huge ripple effect that directly impacts the quality and even the cost of healthcare. Let's just trace it all the way through. You start with no contact bearings. That leads to way less wear and much better heat management. That, in turn, results in a far more reliable tube that just doesn't fail as often. And for a hospital, what does that mean? It means less downtime for the machine, lower service costs, and maybe most important of all, a faster workflow, so they can help more patients more efficiently. A better bearing really does mean better care. It's pretty amazing when you think about it, how an innovation in one single hidden component can completely change the game for a life-saving technology. It really leaves you wondering, if one tiny little bearing can make that much of a difference, what's the next huge breakthrough that's just hiding in plain sight?